So differentiation, this along with integration, forms up the wider field known as calculus. This is very important both at A2 level, and if you go on to study a quantitative based subject at university, you'll be using this extensively as well. So just running you through the structure of this video. So this video is the first in a series of videos looking at your differentiation topic. In this video, we're just going to be looking at your basic differentiation techniques. So as you go through this video, obviously the links are up the top. It is fully navigable, so you can, if you find that you've mastered one technique, you want to look at the more difficult stuff, just using the links up the top to get you where you want to be. So we're just going to start off the video by looking at the principles underlying differentiation. I'm not going to derive the differentiation method from first principles, but I am going to go through and explain what differentiation allows you to do. So if I have this, y equals 5x plus 2, you know that your gradient for this line, so if I'm mapping this in x, y space, your gradient is going to be 5, I'm going to have y-axis intercept of 2. Okay, so straight lines in the form y equals mx plus c, you're going to look at your coefficient on x. This tells you what the gradient on that line is going to be. So in this case, gradient would be 5. Similarly, this one here, y equals minus 3 over 2x minus 7. Here, your gradient, minus 3 over 2. So it's going to be downward sloping. It's not going to be as steep as our previous lines. I'm just going to go through minus 7 on the y-axis. It's going to look something like that. Obviously, I'm not drawing these accurately. Again, you're looking at your coefficient on x, and this tells you what your gradient on the function is going to be. Now, something like this is actually in the form y equals mx plus c, y equals 5. Here, your coefficient on x is actually 0. So if you think, what does y equal 5 actually look like? It's just a horizontal line going through 5 on the y-axis, and here your gradient is 0. That line has no steepness, it is just horizontal. But what about something like this? Y equals x squared. You do know how to sketch this. Y equals x squared. It's a quadratic curve, either going to be U-shaped or N-shaped. It's going to be U-shaped because it's a positive quadratic. Okay, what about the gradient for something that looks like this? Well, you can see here the gradient actually changes. If I draw tangents to this curve, it's quite hard to do on a tablet. Okay, if I've got a tangent there, you can see that that's quite a steep line. It's downward sloping, so it's going to be a negative gradient. Whereas here, I've got a upward sloping line, i.e. a positive gradient. Again, it's quite steep. Whereas if I choose the very base of this curve, so I haven't drawn this very accurate, really that should go through 0, 0. If I draw a tangent to the curve there, i.e. a line touching that curve, you can see that that's going to be a horizontal gradient, i.e. the gradient is 0. So a really important thing to take away from this is that for a quadratic curve like this, and for many other functions, your gradient doesn't remain the same looking all the way along the curve. You can see it starts off negative, gets more and more positive, it's horizontal at this point, and then upward sloping at this point here. So this is what differentiation allows you to be able to do. It allows you to find your gradient at any point along a continuous function like this one here. So let's consider the case of differentiating a function where you have x raised to a single power. So this might be x cubed, this might be x squared, this might be x raised to the power of minus 2 over 3. It doesn't really matter. But if you look at my second line of working here, on the left-hand side, your dy by dx, this is the gradient function. So dy over dx, that is your gradient function. It's also known as your first derivative. But essentially, if you have dy by dx, if you work out dy by dx, then you can work out the gradient of any function at any point along the curve. So on the right-hand side here, this is how you actually work out that gradient function. So essentially, what you're doing here is working in 2 steps. So this is my gradient function on the left-hand side. You're working in 2 steps. So step number 1 here, whatever your power is, you need to bring that power down to the front of your expression on the right-hand side. And then you're going to decrease your power by 1. This might look a little bit confusing, but once we go through a few examples, it's actually very straightforward. So let's do that. So we're going to look at the case where y equals x squared to begin with. Okay, y equals x squared. If I want to find my gradient function, my dy by dx, first step, I need to bring my power down to the front. So 2 goes here. Okay, my x stays an x. And now I need to decrease my power by 1. So that 2 now becomes a 1. Okay, and then of course, anything raised to the power of 1 is just itself. So that's the same as 2x. Now let's consider what happens when I have y equal to 3x squared. Okay, what does my dy by dx, my gradient function, look like now? Well, again, I'm going to bring my power to the front. But now I already have a coefficient on my x squared here. So I need to combine my power, which I bring down to the front, with that 2. So 2 times 3, so multiplication would give me a 6. So that's my new coefficient. And then, as with the previous example, I'm going to decrease my power by 1. That 2 becomes a 1, of course. That's just the same as 6x. Let's take a look at a few more examples. So y equals x cubed. What happens? Dy by dx. Okay, I'm going to bring my power down to the front, which gives me 3x. Decrease this 1 by this 3 by 1 here. 3x squared. Similarly, if I now have y equals, I don't know, 4x cubed, my dy by dx. Okay, I'm going to bring that 3 to the front. Essentially, I need to combine that 3 with my coefficient there already. So 3 times 4 gives me 12x, and reducing that power by 1, 12x squared. Just going to put a dodgy dotted line to delineate our different examples. Okay, a couple of trickier ones now. Y equals x to the half. Okay, my dy by dx here. Well, bring my power to the front. No coefficient there, or my coefficient will be 1, so combine my half with my 1 just gives me a half there. X. Now decreasing this power by 1, what happens when you subtract 1 away from a half? I'm left with minus a half. So now a more difficult example, if I have a coefficient of 7 in front of my x to the half, what happens here? Well, I bring this half out to the front. 7 times by a half leaves me with 7 over 2. And then your power is going to be the same as the power in your previous example there. Let's take a look at a few more. So we're going to look at negative power now, but by now you should see that your rules are going to be exactly the same. Your steps are repeatable. So first it will bring this power to the front, minus 3x, decreasing this power by 1, minus 3 minus 1 gives me minus 4. But now what happens if I have something like this? If I have a negative coefficient, I don't know, minus 4 say, x to the minus 3. Just note here, when I combine these two powers, when I bring this power down to the front, I have minus 3 times by minus 4, which is going to give me a positive coefficient on x. Okay, minus 3 times by minus 4 is positive 12, but the power stays the same. So that's what happens when you have negative powers. And now coming back to the two examples that we looked at right at the start of this video, if I have y equal to a single number, y equals to 7. Okay, here, you remember y equals 7 is just a horizontal line like that. Y-axis intercept 7. Notice horizontal line, it has no gradient. Okay, so your dy by dx is going to be 0 in that case. And that's the same with if I were to have y equal to minus 3, say your dy by dx would also be 0, because you have exactly the same case where you have a horizontal line with no gradient, which means that your dy by dx also has to equal 0. So in this case, your y-axis intercept would be minus 3. And then, so that's the case when you have a constant, y equal to a constant. So you notice we have no term in x here. I do go through this, I do show this, if you apply your rules actually and you consider you consider what happens when you differentiate x to the 0. I do go through this in my notes, I'm not going to go through it here, but you can see why, if you apply your rules, why differentiating this and differentiating this, differentiating a constant will give you a gradient function equal to 0. Now, if I have y equal to a linear function in x, so y equals 3x, or y equals, I don't know, minus 3 over 2x, okay, you know from your y equals mx plus c equation that your gradient here is going to be 3, your dy by dx is going to be 3. Because it's a straight line, obviously that doesn't vary along the curve, so it's just going to be, in this case, minus 3 over 2. Just remember, when you have something in the form of y equals mx plus c, your gradient is going to be that coefficient on x, the number in front of your x. In this case, number in front of your x is 3. In this case, your number in front of your x is minus 3 over 2. So these 2 points here, you could do this algebraically. So for these ones here, when you're differentiating a constant, you could consider the case when x is raised to the power 0. And similarly here, if you think about x, this x here, although there's no power written up there, essentially your power on your x is 1. And if you were to consider both of those cases, you would actually get to these results by applying your rules. But like I said, I'm not going to look at this in detail in this video. I think personally it's just easiest to memorize this. So if you're differentiating a constant, dy by dx is going to equal 0, whereas if you're differentiating a linear term in x, then your dy by dx is just going to be that coefficient on x. So just a quick point on notation now. We've been looking at the case where you have y equal to a function in x. So in this case, let's take a look at y equals x cubed. And when you're working out your first derivative, when you're working out the gradient function, we've been using this notation, dy by dx, i.e. fraction where you have dy on the top and dx on the bottom. Obviously in this case it's going to be 3x squared if you apply your rules. But if I'm given my function in this form here, f of x equal to, and then you have the explicit form of your function on the right hand side. So again, let's look at f of x equal to x cubed. Then when you're working out your gradient function or your first derivative, then the notation that you use is f dash of x. So that's like a little apostrophe there, f dash of x equal to, and then so your working is going to be exactly the same. So this piece of notation here, like I said, it's called f dash of x. It's also known as f prime of x. Essentially it's exactly the same. It's just if you're presented with your function in using this function notation here, then you need to use f dash of x, whereas if your original function is presented like this, where you have y on the left hand side, then you're going to use dy by dx instead. So before moving on to the next section of this video, I strongly recommend that you practice your basic rules. Remember, there's 2 steps. Essentially, you're going to move your power in front, and then you're going to decrease your power by 1 when you're differentiating. What we're going to look at now is the case when you have multiple terms added or subtracted together. So here, if I have y equals 4x squared plus 5x, and I want to work out my gradient function, my dy by dx, all you're going to do is differentiate each of these separate terms in turn. So first of all, looking at this one here, 4x squared, differentiating that, bring my power down, so bring my 2 to the front, 2 combines with that 4, gives me 8. Decreasing my power by 1, that 2 becomes a 1. I'm not going to write a 1 up there, I'm just going to leave it like this. And then plus this term here, differentiating plus 5x. You know, anytime you differentiate a linear term, all you do is take that constant, and that's going to be your first derivative of that term, so plus 5. Okay, just quite simply differentiating each of those terms one by one to give me my final result. Let's look at a couple more now. Y equals 3x cubed plus 7, say. My dy by dx here differentiating that first term, bring that 3 to the front, minus the other 3, which gives you 9x, decreasing that power by 1, and that 3 becomes a 2. Now looking at this second term here, what happens when you differentiate a constant? It disappears. So I could put plus 0, or I could just leave it like this, and I'm just going to leave it. Now a longer example, y equals 3x to the minus 2 plus x squared minus 6. Here, dy by dx, again applying those same rules, differentiating each of my terms one by one. Bring that minus 2 to the front, 3 becomes a minus 6. X decreases power by 1, minus 3. Okay. Looking at the second term, bring this 2 to the front, this will be plus 2x, so decreasing this power by 1 here. A 2 becomes a 1, don't need to write that 1 up there, it's just the same. And then differentiating my constant term here, minus 6, just disappears. Okay, that differentiates away to 0, so I can just leave it like that. But important thing to notice here is that when you have multiple terms added or subtracted from one or another, all you're going to do is differentiate each of those terms one by one. Thanks very much for watching, and don't forget to subscribe for more tutoring videos. Remember that full notes and other resources are available on my tutoring website at idktuition.com. And if you'd like me to cover anything in particular, please leave me a message in the comments below or on Twitter at TomDavies32.